Okay, so today we will talk about what is called convex set and functions in optimization. So first of all, why do we care about convexity in optimization? So actually what matters more in optimization is convexity versus non-convex, rather than linear and nonlinear. There is a particular reason for that. So I will first explain in the first few slides why do we care so much about convexity, right? Intuitively, what you can see from this the first figure here, I have drawn a convex function and a non-convex function, right? So without telling you what is a convex function yet, as you can see in the first picture, there is one minimum, right? So this minimum is a global minimum of this function. Well, on the other hand, for this non-convex function, there are two local minimums, right? And the local minimum may not necessarily be global minimum for non-convex function, right? That's why convexity is so important. Then let's give two definitions using some of the notations we introduced in the previous lecture when we talk about calculus. So we say a point is a global minimum of f of x if for all x in the domain, this fx star is less than or equal to fx for all the x in the domain of f. And then we see x node is a local minimum of f of x if there exists a delta greater than 0, such that for all the x within the distance of within delta distance of x0, we have fx0 less than or equal to f of x, right? So within a small, let's say a unit ball with a length delta, then for all the x in this neighborhood, x0 is a minimum, give you the minimum, right? So that's the difference between global and local minimum. Local minimum is within a small domain, and then global minimum is within the whole domain. Okay. And then what are convex sets and functions? So here's a slide to summarize the definition of a convex set and convex functions. So we say a set is convex if you take two arbitrary points, x and y. So here x and y are both in Rn. Then you draw a line segment between these two points. Okay, and if you for any arbitrary 2 points you pick from the set C, the line segment is also in C. Right? So the line segment can be denoted as lambda x plus 1 minus lambda times y, where lambda is from 0 to 1. Okay. Here, as you can see, this set is clearly a convex set. Pick any arbitrary 2 points in this particular set, draw a line segment. The line segment is also in the set. But here, if you pick this set, pick these 2 points, the whole line segment is not always in the set, right? So this set is not a convex set. Similarly, you can make an analogy to convex functions. The idea is the following. If you have a function f of x, then pick any arbitrary 2 points. Of course, the domain of f has to be a convex set, otherwise you cannot even define the convex combination. Okay. And then if the following inequality hold, what does this inequality mean geometrically? If you pick two arbitrary points and then draw a line segment between these 2 points on the function, this line segment is always above the curve. Right? So this curve is below any arbitrary 2 points you pick. So algebraically, you can say, I pick x and y, and then I take lambda plus 1 minus lambda y. This is like the convex combination of these 2 points. This is the line segment evaluated using function f. That will be the left-hand side give you this curve here, right? And the right-hand side is nothing but a convex combination of the function values. So the right-hand side gives you actually this curve here. Should be pretty clear to visualize compared with this algebraic expression. right? And lambda can be between 0 and 1. So when lambda equals to 0, you are staying at this particular point. When lambda equals 1, you are at this point. So then as lambda goes from 0 to 1, you are covering the whole line segment. Okay. Yeah, so that's that. So before we go to the sort of the details of this lecture, I want to give a sort of like a roadmap on what we will cover in roughly the first half of the semester. We will talk about different subclasses of convex optimization, how to solve them, and their properties. So what is a so-called a convex optimization problem, right? The most general way to express a convex optimization problem is the following, where you are minimizing f of x, where f of x is a convex function. And then you have a bunch of constraints with linear inequality, not linear inequality, but arbitrary inequality constraints and equality constraint. So if the domain, what is the domain here? That means the domain of the function f intersected with the domain of each of the constraints, right? Those constraints have to be defined in order for this optimization problem to be defined. Okay, so the domain is convex, and then this is a convex optimization problem, provided that the function f is convex, all the inequality constraints are convex, and all the hj constraints are linear constraints, right? I will explain in a second why they have to be linear. Okay. So this is a general convex optimization problem. I will not spend the whole class just focus on convex optimization problem. If you are interested in more details, you could take this class from industrial engineering. I think it is co-listed with AAE as well. Okay, so if you want a more detailed introduction here, they will spend the whole semester just talking about this problem. Since we want to cover other topic, we won't be solely focused on this type of problem. Okay, so the takeaway is that for convex optimization problem, you have f being convex, the domain is convex, and this constraint describe a feasible set which is also convex. Right? So in general, you are optimizing a convex function subject to constraints that define a convex region. That is a convex optimization problem. Okay. So at high level, why do we care about convex optimization problem? So this has to do with computational complexity. How many of you have taken a class in computational complexity before? Like how to prove a problem is NP hard and so forth. Okay, maybe not. But that's something you could consider as if you are doing a PhD related to optimization or computer science. This is something you would like to know, although you may not be doing a PhD in computational complexity. Right? So this is something that is worth knowing. Okay, so why convex optimization problem is special compared with others is because convex optimization problem can be solved in polynomial time. Right? So I give you a problem with size n, right? So n can be the number of variables and constraints. It has been proved that if the problem is convex, then I can come up with an algorithm or any sort of oracle that give you the global optimal solution for this convex problem in terms of polynomial times the evaluation with respect to the problem size, right? So if you are familiar with, let's say, algorithm in general, there are many problems that can be solved in polynomial time, right? So if I give you n numbers and ask you to sort those n numbers, right, from the largest number to the smallest number, you know that the computational complexity is n log n, right? So then, n log n is a polynomial solvable problem, right? And convex optimization is also polynomial solvable. And in contrary to polynomial solvable problem, there is a definition called non-deterministic polynomial time. Right? Note that NP is not, it does not denote not polynomial, right? It means non-deterministic polynomial. Okay, so in order to fully understand what NP means, you should take a course on computational complexity or algorithm. Let me just explain to you the intuition in words what NP means, right? So as I said, a polynomial time means you can find a solution of a particular problem in polynomial time with respect to the problem size. NP means you can verify a given solution in polynomial time, right? So let me give you an intuitive example. So let's say you want to decide whether there is a 2-hour route from here to Chicago, okay? And then, of course, there are different streets you can take. You can represent, let's say, the streets as edges in a graph, right? So if I ask you the following question, does there exist a 2-hour route from here to Chicago? If I can find you a route in polynomial time with respect to the number of streets from here to Chicago, then that is a polynomially time solvable problem, right? Because I directly gave you a solution. So now, if imagine the other case, if I can say, pick a route from here to Chicago, and then I can validate that in polynomial time, whether that's less than 2 hours or not, right? So as you can see, this validation or certification problem is an easier problem than finding a route less than 2 hours, right? It's like I give you a particular route, tell me whether it's less than 2 hours or not, okay? That's called if you can validate any particular instance or particular solution in polynomial time, that is called an NP problem. Okay, so of course, P is a subset of NP because if you can find a solution, of course, you can validate the solution in polynomial time. Okay. Yeah. So what is called NP hard problem? So NP hard problem is a subset of NP problem that is the hardest to solve, right? So if you can show that an NP hard problem can be solved in polynomial time, then all the NP problem can be solved in polynomial time, right? Okay, so then next question to ask is P equivalent to NP, right? Are these two things equivalent? It is a problem that has not been solved yet. Actually, it's a sort of a century challenging mathematical problem. Maybe I remember there was like a mathematics institute. They raised 7 or 8 different problems that are the most challenging mathematical problem of this century. Things like Riemann hypothesis, Navier-Stokes equations, and then P equals to NP is one of them. Okay, so if you can prove P equals to NP, you can get like $1 million prize from this institute. Okay, so so far it has not been proved whether P is equals to NP or not, but most people tend to believe P is not equal to NP. Okay, in other words, if a problem is NP hard, we just assume it cannot be solved in polynomial time. Okay, so in other words, if you feel P is not equal to NP, which is this left diagram here, then you can argue that convex optimization problem is really different than the rest of the optimization problem, because if you consider these optimization problems which are non-convex, with mixed integer programming, non-convex QC, QP, MNLP, it has been proved that these problems are NP hard in general, but convex optimization problems are polynomially solvable. Okay. Yes.
So when you say polynomial time, I still have, so the computation time could be written in the form of polynomial. Is this?
Oh yeah, so for example, I give you a convex optimization problem, let's say with n variables and m constraints, right? And then I can compute the optimal solution of this convex optimization problem in terms of a polynomial function of n and m, right? Like n raised to the power of 3, m raised to the power of 5, right? It's not exponential, right? Yeah, okay. Yeah, you can think about intuitively, it's like a polynomial function rather than exponential function, right? You know that asymptotically as n and m grows larger, exponential function will always outgrow a polynomial function. Yeah, so that's sort of the intuition behind it. But rigorously speaking, exponential is not equivalent to NP hard. It's another class of optimization problem. But then intuitively, you can think about it that way. Okay. Other questions? Yeah.
Yeah, I'm a bit confused.
Yeah.
Isn't it kind of from definition that P is a subset of NP in the sense that if we can solve them in polynomial time, surely we can verify it in polynomial time?
Yeah. So if this part is true, P is a subset NP, as you can see here, right? So P is here,
okay.
and then NP is here, but it has not been proved yet. So some people believe P equals to NP.
Okay.
Yeah.
So in any case, we know that P is a subset of
yeah. But we don't know if it's a true subset.
P can be solved.
Yeah, exactly. Yeah, but it has not been proved yet. Okay. Yeah. In reality, when you have a particular problem, it doesn't mean computationally an NP-hard problem is always harder than a polynomial problem, computationally. Because the constant and the polynomial order does matter for a finite problem. It just asymptotically, as problem size goes to infinity, exponential is always worse than polynomial. But then in practice, you are always solving finite size problem. It could be some of the polynomial side optimization. Some of the convex optimization problem are even harder to solve than non-convex optimization problem in reality. Okay. Yeah, but this is like a theoretical argument why convex problems are so special. Okay. All right. So I don't want to spend too much time on this, but this is just to give you some idea why we care about this. Okay, so before we introduce some properties of convex set, I want to give you sort of a cheat sheet for combination of points. Because I always get confused myself when I study those concepts, so therefore I decided to summarize this concept in a single slide and with some geometric intuition. So from the last lecture on linear algebra, you are aware of what does linear combination of vectors mean, right? It simply means you take the combination of lambda I xi, where there are no restrictions on lambda, right? As lambda can take any real values. So you can also imagine what convex combination means, because I told you convex combination is like drawing a line segment between points, right? So here, let's assume you pick n points. Then convex combination means taking the summation lambda I xi, where all the lambda I has to be greater than or equal to 0, and then the lambda has to be sum equal to 1. Okay. And I find combination is something different than convex combination. We also have the lambda sum equal to 1, but lambda is not restricted to be non-negative. Okay. And there is something called Corny combination, where we have lambda I greater than or equal to 0, and there are no more restrictions on lambda. Okay. So we will also cover some Corny combination in probably lecture 7 or 8 of this class. But I want to put this cheat sheet here so that you can refer to this cheat sheet later. Okay. But then when you read those definitions, it's really non-intuitive, right? Each time you read it, probably next time you'll forget about it. So let's see. Wait, I don't have this slide here. Okay. So yeah, so I do have this slide. I will do that later. Okay. Yeah. So here, let's consider this this particular claim here. So I said a convex set means if you pick 2 points, their convex combination is in the set, right? That's the definition of a convex set. But this claim is saying if the set is convex, you pick any arbitrary n points, their convex combination must also be in C. Okay, so this is a generalization from picking any arbitrary 2 points to picking any arbitrary n points and take their convex combination. Okay, so why this is true? You can think about how do we prove that, right? So the claim is whenever you pick 2 points, take their convex combination, this line segment is in the set. Now I'm saying if I pick n points, take their convex combination, it's like so let's say if you pick 4 points, take their convex combination, that would be this this whole polyhedral set formed by these 4 points, right? So if you pick any 2 points in the set, pick any arbitrary points, take their convex combination, they are also in the set. So how do we prove this claim here? When you try to generalize from 2 to arbitrary endpoints, what will be the proof technique we should be using?
By contradiction, maybe?
By contradiction.
If we assume that there is like a point inside which is not in the set.
Induction.
Yeah, so induction would be the way to go. So induction would be, you already know n equals to 2 is true, right? So how do you prove any arbitrary n is true? That is called induction. You already have the base case. So the base case n equals to 2 is true. You already know that, right? So now with induction, we can have our what is called like induction hypothesis, right? So that means for n minus 1 points, their convex combination, let's say I from 1 to n, n minus 1, xi is in the set C for any arbitrary lambda sum to I from 1 to n minus 1, lambda I greater than or equal to 0, right? So now we want to assume this is true. We want to consider the convex combination of any arbitrary endpoints, right? So what we want to show is for any, let's say x1 to xn, let's consider their convex combination. Let's use a new letter, maybe let's say mu I xi. I will write it out as f from 1 to n minus 1 plus, let's say mu n xn plus this, right? Okay, so how do we use this fact to prove this part, right? Because you already know, you already know that for any convex combination of n points, n minus 1 points, it is true, right? So you want to construct some sort of convex combination of n minus 1 point. One of the things you could do is, let's say you take mu n xn plus, let's say you multiply by 1 minus mu n, and then I from 1 to n minus 1, mu I divide, because you multiply by 1 minus mu n, you also divide by 1 minus mu n times xi, right? So clearly you can see that this part is a convex combination of n minus 1 point, right? Because their coefficient will sum up equals to 1, right? So therefore, due to the induction hypothesis, so this guy belongs to C, right? Because you can check their coefficient sum to 1 because you scale them by 1 minus mu n. So this guy is in C, and we know xn is in C, and this is a convex combination of 2 points in C, right? So therefore, this point is in C. Okay. Any questions for this simple proof? Okay. Yeah. So that gives you whenever you want to prove a claim, first think about maybe what techniques you should use, right? From 2 to n, then usually you would be thinking you will be using induction. Okay. So you can read this proof here as well. Okay. Yeah. So now this is a picture I want to show you the intuition of convex combination, affine combination, conic combination, and so forth. So here's the definition. When we see, let's say we are given a set C, how do you define what is called convex Hall, affine Hall, conic Hall, and linear Hall, or linear span of this particular set? So convex Hall is what is so-called the smallest convex set that contains all the elements of C, right? So if you consider the smallest convex set that contains all the elements of C, you could just take all the possible convex combinations of C, elements in C, right? Because if it's a convex set, all the convex combinations of elements in C must be in that convex Hall. So that will be the smallest convex set. And similarly, affine Hall, conic Hall, and linear Hall, at the smallest affine conic and linear subspace that incorporate this set. Okay. Again, this could be quite non-intuitive, but I think it will be better explained with this geometric interpretation. So let's consider a problem in 2D where we have these two points here, right? So this set is very simple. It only has two elements, okay? So if you consider the convex hull of these 2 points, it is nothing but the line segment between these 2 points, okay? And if you consider the affine hull of these 2 points, remember that in the definition of affine combination, we have lambda 1 x1 plus lambda 2 x2, where lambda 1 plus lambda 2 equals to 1. But we don't have non-negative constraint on the lambdas. So therefore, it will be this whole line instead of the line segment because we don't have constraint on lambda, okay? And then for conic hull, remember the definition is lambda 1 x1 plus lambda 2 x2, where lambda 1, lambda 2 has to be greater than or equal to 0. Right? There are no like sum over to 1. So therefore, it will denote this green region here, right? Okay. And linear hull is simple. You are taking linear combination of these 2 vectors. Since these 2 vectors are linearly independent, that spans the whole R2. Okay, so this picture should tell you intuitively what convex, affine, and conic and linear combination means, right? So this is like a side note because we will only be covering this part for this lecture, but I want to put it here such that you can refer to these slides when we go to the next few lectures. Okay.
How would a fine hull look like if it was 3 points? So everything else, I think it's clear.
Yeah, so I find if there are 3 points here, I think it is the whole R2 plane. If they are sort of affinely independent. So if you draw another point here, I think it will be the whole R2.
Okay.
If the point is here, then you are still on this line segment. Yeah. Okay.
And these 2 points, you have assumed that they are linearly independent to each other.
So if you are talking about the linear hull, they are linearly independent. If they are sort of on the same line, then they are linearly dependent. Then you are talking about straight line rather than the whole space. Okay. Yeah. So you could try to play with it and try to absorb what it looks like geometrically. Okay. Yeah, so next I will give you some examples of a convex set. So how do you really validate whether a set is a convex set or not? The easiest way to do that is by definition, right? So how to a set is, let's say, convex. Right. Usually the solution is check the definition. Right. Meaning that pick any arbitrary 2 point from this set and prove that the convex combination is still in this set. Okay. So let's go through some examples. Of course, you could start with some trivial ones like empty set, a point, or a line. Right? They are clearly convex set. So let's try to think a little bit about why a norm ball is a convex set, because we talked about norms, vector norms in the previous lecture. Right? So remember, what properties does a norm function have? There are 4 properties. Right? Let's try to remember. The first is it has to be non-negative. Right? Second is that it is 0 only when you are evaluating a 0 vector. Third is if you multiply a vector by a scalar, you can take that the absolute value of that scalar out. The fourth thing is triangle inequality. Right? So we will be using these 4 properties to show that actually probably we only need 1 or 2 of those properties to show a norm ball is a convex set. Okay, so by definition, what we need to do is let's say, pick any arbitrary point, x and y, in the set where, let's say, I would just denote it as x, the norm of x is less than or equal to r, right? Right, so now what we need to show is that the convex combination of x and y also satisfy this property here, okay? So let's take the convex combination of x and y, okay? So the convex combination would be lambda x plus 1 minus lambda y, right? So we want to show that this guy is also less than or equal to r for any arbitrary lambda between 0 and 1, right? So if this guy is also less than or equal to r, then we know this convex combination of 2 points are also in the set, okay? So yeah, so we would use triangle inequality, right, as you said. So by triangle inequality, we know that you can treat, let's see, these two as two separate vectors. So then it is less than or equal to, let's say, lambda x plus 1 minus lambda y. Okay. Now, what do you do next? Yeah, you can take lambda out, right? Because lambda is a scalar. So this is nothing but lambda x plus, 1 minus lambda y, right? So because the normal x and normal y are less than or equal to r, then this thing is less than or equal to r, right? So now we are done with that. Okay, so you can verify using the definition the next few sets are also convex set, right? You can check a hyperplane is a convex set, half space is basically a single constraint A transpose x less than or equal to b, and then affine space meaning you have a matrix m by n matrix ax equals to b. So polyhedral means you have a matrix multiply x less than or equal to b. So b is also a vector, and then assume the inequality is applied component-wise, right? So you have m constraints, n variables. Okay, so this means basically, let's say ai transpose x less than or equal to bi, or yeah, let's say it's a1 all the way to maybe am x transpose x less than or equal to b m, right? So there are m of those half space constraints. That is called a polyhedral set. Okay. So one of the things to note that this is also a polyhedral set. You have some inequality, some equality, but then you can always convert equality to two inequalities, right? Less than or equal to, greater than or equal to, and then you multiply -1 on both sides. They both become less than or equal to 2. So this is what is called linear programs. If you have a constraint of this form that is called linear program, we will spend maybe 3 lectures on linear programs itself. Okay. All right. Then let's talk a little bit about the concept called operations that preserve convexity. Right? The motivation of this is maybe each time you want to check whether a set is convex or not, you don't want to check definition all over again, right? But there are some operations. If you apply those operations to a convex set, that retains convexity. Right? So if you show that those operations can preserve convexity, you only need to show that the first set is convex, and then apply this operation that remains convex. So there are some simple operations that preserve convexity. You can also check by definition. Right? If you have, let's say, intersection of convex set is convex, it should be very easy to prove even algebraically, but geometrically you can consider, let's say, two convex set. Then you consider their intersection, that is also a convex set, right? And scaling and translation means if you C is convex, And then if you scale C by A and B, where A and B are two scalars, that remains convexity, right? I mean, you apply a linear transformation to the convex set, that remains linear. So here is without loss of generality. If you apply like an affine transformation AX plus B, then if C is convex, after this linear transformation, the set remains convex. Okay, and similarly, the inverse of this transformation is also convex. You could try these properties in your homework question. I wouldn't be able to do all the proofs in class. I want to just focus on a couple of proofs that may give you some insight. Okay, you could verify by definition those operations preserve convexity. And there are two, maybe the last one is less commonly used, but the perspective function is useful in optimization. The idea is you have a n plus 1 dimensional set, okay? So the set lives in n plus 1 dimensional space. You can divide it into Rn and positive R plus that denote as a R plus plus. If you take the ratio of the first n-dimensional vectors by z, that preserves convexity. That is called perspective operation, where you scale the first n elements of your vector by the last vector, which is strictly positive. Okay, that retains convexity. Showing that is not so straightforward, but then you could use a definition and check that. I won't do that in class. And similarly, linear fractional images and pre-images also retains convexity. Okay, you can think about this as a composition of a linear operation and a perspective operation, where the denominator has to be strictly positive. Okay, so you can take the ratio of two linear functions. Okay. Yeah. All right. I won't spend the proof proving those properties, but then you could check after class or even try some. I don't remember if we assign this as homework problems or not. Okay. So that's what we want to talk about for convex set. We want to prove some properties for convex functions here. Okay. Any questions so far? Okay. Yeah. So now let's go to convex function. If you didn't follow what I talk about here, it's totally fine because I skipped through those very fast. You could read it after class. It shouldn't be too difficult to read. Okay. So now let's reset your mind, and then we will go to convex functions here. Yeah, again, just to remind you the definition, convex function means for any arbitrary x and y, and then you draw a line segment, it's always above the curve of this function, okay? And algebraically, it means this formula here. Okay. Yeah, and then there's another definition called concave function. That means if you draw a line segment, it is always below the curve, right? So if a function is convex, you can easily show that minus f is concave and vice versa. Okay. Then there are a few other properties. One is called strictly convex. Okay. So instead of saying the line segment is greater than or equal to the curve, this is saying this line segment is strictly above the curve. Okay. Can someone give me an example where a function is a convex function but not a strictly convex function?
Not strictly.
Yeah, not a strictly convex function, but it is a convex function.
Line.
Yeah, like a linear function, right? So a linear function, of course, you draw a line segment, it is a line itself. It is greater than or equal to the line, but it is not strictly convex because you don't have this strict greater than here. Okay. So in words, a strictly convex means that it should have a bigger curvature than a linear function. So that means strictly convex. And there is something called strongly convex, where by definition there needs to be a parameter m greater than 0 and f minus m over 2, the 2 norm of x, or maybe I should write this as a 2 norm of x, is convex. So that means if you deduct a quadratic function from that function is still convex, right? So in words, that the strongly convex function means it is at least more curved than a quadratic function. Okay, so again, strongly convex is stronger than strictly convex because it has to be more curved than a quadratic function. And strictly convex is stronger than a convex function because it has to hold strictly. It cannot be a linear function. Okay, that's by definition. Probably you will see this concept in some of the literature, but I want to give you this definition here. All right, now it comes to probably the most two important theorems in this class, which is called the first order characterization and the second order characterization of the convex function. Okay, so the motivation of doing this is the following. When you are trying to show whether a function is convex or not, of course you could check the definition. Are there more convenient ways of validating a function is convex, right? So the first property is using the first order information. As long as it satisfies this first order property, we know that the function is convex. And then the second property is using the Hessian information. As long as it satisfies that property, you know the function is convex, right? So in other words, we are giving you 3 different tools to validate a function is convex. The first toolbox is by definition, right, using the lambda combination. You can regard that as a 0th order characterization. We are not using any gradient. But now, if you can use a gradient, what will be the necessary and sufficient condition to say the function is convex? Then if you can use a Hessian, what will be the property of the Hessian for a function to be convex? Okay, so that's what we will talk about in the next few slides. All right, here, this formula gives you the first order characterization of a convex function. Okay, geometrically, what does that mean? So let's check this, this function here. Clearly, it is convex. Now, the first order condition means if you pick a point here, right, and then you draw the gradient at this point. So the gradient gives you this particular linear function, right? So if you use a first order Taylor series approximation per se, right? So that gives you this function. So this first order Taylor series approximation at this particular point always underestimate the function. That's what geometrically this means. So here, as you can see, the right-hand side is like the first order approximation, right? You have a Taylor series expansion at f of x, and then take the gradient out of f of x, and then for any arbitrary perturbation, you can think about you make a perturbation to x by taking y minus x is how much you are going to perturb x, right? But then if you take this first order approximation, it is always smaller than or equal to f of y. That's what this means in a geometric sense. Okay. Now we are going to prove this. Any questions so far for the definition? Okay. So let's show it real quick. Be here. Okay. So let's say we first prove one direction, right? So if a function is convex, then that implies fy greater than or equal to f of x plus the gradient transpose y minus x. Okay. Yeah. So how do we, so any intuition on how to show that? You don't need to think about a complete proof because for a complete proof, you need to write it down on a piece of paper, right? So this proof is saying like the zeros order, so if let's write down the property of a convex function first, which is, let's say, lambda y plus 1 minus lambda x less than or equal to lambda f of y plus 1 minus lambda f of x, right? So this is a sort of the zeros order property, right? Because that's what we have so far. We only know the definition of convexity. So it says the zeros order characterization implies the first order characterization, right? So how do we show that? Roughly. Because intuitively you would think about how do you get the gradient here, right? Because you don't have any gradient here from the definition, but then you could try to play with this to somehow get a gradient, right? As you can see, when the definition of the gradient is you take some small values closer to 0 and let it divide something, for example, divide it by lambda and let lambda goes to 0, and that gives you some gradient, right? So here you could play with this equation a little bit. Let's say, so you could rearrange this the left-hand side a little bit, saying we have f of x plus lambda times y minus x, right? Okay, so you can think about this as starting from x and taking the direction y minus x and perturb it by lambda, right? So if you divide this by lambda, this will give you, you use this minus fx and divide by lambda, it gives you the directional derivative at direction y minus x, okay? So let's maybe let's move fx on this side. So minus f of x, you could check the algebra here. Then the right-hand side remains lambda times fy minus f of x, right? So now, as you can see here, you have the difference of this guy, which is saying we start from x and then we move in the direction y minus x by lambda, and then minus fx, which is saying how much this thing will change when you go around the direction of y minus x by length lambda. And then you have lambda on the side. You could divide lambda, and then that lambda goes to 0. Right? So you, let's say, divide both sides by lambda and set lambda to 0. So let's say limit lambda goes to 0 plus lambda y minus x minus f of x divided by lambda less than or equal to fy minus fx. Okay. Now look at this term. What is this guy? It is the directional derivative of this function at x in the direction y minus x. Right? So we didn't talk about directional derivative in the last lecture. So the definition of, let's say, directional derivative, so let's open a box here. Is let's think about function evaluated f of x, and suppose x is in Rn, and then you have a vector v in Rn, right? So direction derivative is, let's say you have limit h goes to 0, fx plus h times this vector v minus f of x divided by, oh no, I wrote infinity, h. Okay. So how to calculate the directional derivative is nothing but the gradient of f of x transpose the vector v, right? Because a gradient describes how much this function value will change if you perturb each of the entries x1 all the way to xn by unit length, right? But now you are perturbing the x by v, right? So if you go direction v, then that should give you this gradient transpose v. So here, if you apply the directional derivative here, that means the gradient of fx transpose the direction here is y minus x, less than or equal to fy minus fx, right? So that is exactly the same thing as what our claim is. Okay. Okay, so you could read a little bit about it and try to absorb it after class. And then we can also show the other way around. The other way around is relatively simple. I will just show you the type note. So this is the, this is the proof. And then you can also show the other way around, okay? So the way to show the other way around is you could consider any x and y and consider a point z, which is a convex combination of x and y, right? And then you apply the first order condition at point z, right? With respect to x and y separately, and takes a convex combination of these two inequalities, then the gradient term will cancel out. So after you cancel out the gradient term, you arrive at the definition. Okay, those are just algebra. If you sit down with a piece of paper, this is very straightforward to do. Okay. Now, I want to spend some time on proving the second order condition because that's slightly more interesting than the first order condition. So here, if f is twice differentiable, like a quadratic function, right? So here I'm plotting a quadratic function, then the necessary and sufficient condition for f being convex is the Hessian of this function is positive semi-definite. Okay, so here, this notation means the Hessian is positive semi-definite. Okay. Yeah, so intuitively, you can think about when the second order derivative is positive semi-definite, maybe you can think about the intuition in 1D, right? The second order derivative is non-negative, right? That means the derivative is increasing, right? As you can see here, for this quadratic function, its derivative keeps increasing, right? And that gives you a convex function, and if you consider the second order derivative, it is always non-negative, okay? So that's sort of the intuition, but then to prove that rigorously is not so straightforward. I will show you sort of a simplified proof by assuming the second order derivative is not only differentiable, but also continuous. In other words, I will show you a special case where f is a C2 function. C2 means second order derivative exists and is continuous, right? And then in the one of the reference of the book, it shows you in general without assuming continuity, but that is a much more lengthy proof. I give you a much shorter proof, okay? Yeah, so let's, oh yeah, this is the notes. Maybe I'll prefer to write it down step by step. Otherwise, if I show you the whole proof, it is very overwhelming, okay? So let's prove one direction, meaning, let's say, convexity implies the Hessian being positive semi-definite for all x. Let's just drop the domain of f because let's just assume it's in Rn, or the domain is convex. Okay. Now, if you are not so fluent with linear algebra, you may get confused with positive semi-definiteness when you first play with it, right? So let's first remind you, what does PSD mean? So positive semi-definite of a matrix means for any vector P in Rn, we have P transpose the Hessian of f P always it has to be greater than or equal to 0. Okay, that's what the positive semi-definite mean. Okay, so as you can see, to validate this property, right, we want to show that convexity, maybe from using the zeroth order characterization, from property of the convex, definition of the convex function, we want to show that for any Hessian you give me, right, and then you need to check for any vector P in Rn. This guy has to be greater than or equal to 0, right? It is not so easy to validate, right? Because you need to check for all the vector. For all is not so easy to argue. On the other hand, if you use a trick, let's say proof by contradiction, right? You can use a reverse negation of this claim, right? What is the negation of this claim, right? For all x, this matrix is a positive semi-definite, right? So this means for all x, for all the vector P in Rn, this thing has to hold, right? What is the negation of this claim?
There is a P where it is less than 0.
Yeah, right, exactly. So the negation is much easier to do, right? You only need to pick a particular x, and then just need to pick one x. Doesn't need to show for all x, right? Pick one x and pick one P. It is not PSD, right? Right. And then you show that if this hold, the function is not convex. Then you prove this property. That's a reverse negation of this claim, right? So the idea is we want to let's say pick an arbitrary x and then pick a P, vector P in Rn. Then we are this property does not hold when this property does not hold, meaning that there is a P such that it is not positive semi-definite, right? So that is a negation of this property. Okay, it only has to pick one x, one P. This property does not hold. And then we can find some contradiction with the fact that this function is convex, right? So our goal is we find this this negation, and then we show that f is not convex. Then we are done, right? This is like proof by contradiction. Okay. Yeah. So let's assume we have an x, and then we have a p, right? And then this this Hessian metric is not positive semi-definite. It's actually negative, right? Then you can try to construct something that violate the convexity property, right? That's the idea, okay? So here, let me go to the, I don't want to write it down anymore, okay? So here we will use some property, again, just to rephrase that. What we did is assume there exists X node such that this is not positive semi-definite. That means we can choose a vector P such that this thing is negative. That's our idea, right? Now you want to do something that shows this function is non-convex, right? So intuitively or geometrically, this argument means there exists a direction P such that if you consider the function on this direction P, the curve is not convex, right? If you do the second order Taylor series expansion on direction P, this curve is the other shape around rather than a convex curve, right? So intuitively, what you can do is show that on this curve, the convex property is violated, right? Because you know the second order Hessian is not positive semi-definite, okay? So that's sort of the intuition of that. Now, so here's where my assumption comes into play. Because I assume the Hessian is continuous, right? So if the Hessian is continuous, I can argue that in a small neighborhood of x0, this guy remains to be negative, right? Because this function, the Hessian is a continuous function, right? And P is a fixed vector. PR is some number, right? So if you consider this continuous function, since it is negative at x naught, it remains to be negative in a small neighborhood of x naught, right? That's a definition of continuity, right? Okay. So because it is continuous, I can pick a very small scalar delta greater than 0 such that this guy remains to be negative for all the t in this smaller range, right? That's a continuous property. So now I can argue on this small range, convexity is violated, okay? So what I would do is let's use the mean value theorem from calculus. Remember the mean value theorem is actually you can also call it Taylor series expansion with the Lagrange form, right? So if you consider a perturbation of x0 to delta plus p minus delta times p, okay? So consider a plus and minus perturbation, right? It's like I have let's say I have geometrically, I know that assume this is a p direction, right? Now I'm only consider the function at the p direction. I know the Hessian is not positive semi-definite in the p direction, so that I know that this function looks something like this at this particular point x0. Now I want to show rigorously that convexity is violated in this direction p, okay? Then I could perturb a little bit by delta because I know the Hessian keeps to be non-positive semi-definite when I perturb it a little bit by, let's say, minus delta p and delta p, right? Just perturb it slightly. Now I have 2 points. What I need to show by definition is that this 2 point is lower than the curve. That violates the definition of convexity. That's what essentially I'm doing here. So if you do the Taylor series expansion, at x node, you can have the exact gradient here, but then in the second order, you know that because of the mean value theorem or Taylor series expansion with Lagrangian remainder, you know that although the second order won't be exact, you know there exists a T1 that is between 0 and delta such that this approximation is exact, okay? And then similarly, there exists a T2 such that this approximation is exact. So now you sum over these two terms, the first order terms will cancel out. Okay, so what you are left with are those two second order terms. Right? Because you know the Hessian times P transpose the Hessian P remains to be negative by the continuity property, this guy is negative, this guy is also negative. So now you have to find a contradiction. Okay, the function is not convex, at least in this particular direction P, where P is like a certificate that the Hessian is not positive semi-definite. Okay, so that's sort of the high-level intuition, and then you can check the math as well. Yeah, so let's give folks some time to absorb it a little bit. Okay, so again, just to summarize the idea of this proof, we want to show the Hessian must be positive semi-definite. But showing that is not straightforward because to certify the PSD property, you need to check all the vector in Rn such that P transpose the Hessian P is non-negative, right? Checking all the vectors are hard. It's easier to show that by the reverse negation of this claim, where you only need to pick one vector that violates the PSD property, and show that if the the vector that satisfy the non-PSD property gives rise to the violation of convexity, then you know that if convexity must imply the Hessian being PSD. Okay. Yeah. Okay, so that's that. And then the reverse direction is a bit easier to show, where you could show that the second order characterization implies the first order characterization, right? Because we already show first order and the definition are equivalent. If the second order imply the first order, that implies the definition as well. Okay. So here you could just use mean value theorem again from calculus, since you take any two arbitrary point x and y, then you have this like the Lagrangian remainder term here, right? Because this Hessian is always positive semi-definite, you know this part is always greater than or equal to 0, and that implies a first order characterization. Because this is greater than or equal to 0, this is strictly equal, then we imply this term here. Okay, yeah. All right, so now let me give you a few examples of a convex function. First of all, think about how do we show a function is convex, right? So now you have three ways to show whether a function is convex or not, right? So first is definition, right? Just check, take two vectors, take the convex combination and show this line segment is above the curve, right? So you could do it by definition. The first order property is not used very often, because if you can take the gradient of this function, typically this function is always differentiable as C2 as well. Most of the function, if it's C1, it is also C2, right? So therefore, you don't use the first order characterization very often. So either it's definition or use the second order characterization, right? With the second order characterization, you only need to calculate the Hessian and check the Hessian is PSD. Right? You can apply this concept to all the functions in this slide. All these functions are differentiable functions, right? So what you can do is just take the Hessian of those functions and show that the Hessian is PSD. Okay, so the first set of functions are those univariant functions, right? What you can do is take the second order derivative of those functions, like the exponential function, right? Take second order derivatives and show that second order derivative are non-negative. Right? That should be straightforward. And then affine functions, yeah, that should be straightforward. The second order derivative is like 0, right? And then quadratic functions, right? We have x transpose qx plus b transpose x plus c. This is clearly convex if q is a positive semi-definite, right? Because the hashing of this function is q itself, right? When q is a positive semi-definite, this is a convex function. So here, least square loss, it is also convex because clearly least square loss is a quadratic function, right? You take the 2 norm, that means you are taking y, this is essentially y minus ax transpose y minus ax, right? So the quadratic function, the Q matrix here is A transpose A, right? You can easily show that this matrix is PSD. Okay. Then the norm function, you can think about this as an analogy with why this norm set is a convex set, right? And similarly, you can show the norm function is a convex function just by definition. So support function, when I first read it, it is very non-intuitive, but you can think about the geometric interpretation of the support function. Okay. Here, consider any set. The set does not need to be convex. So its support function is saying, I give you a value x. Now consider the maximum of y over this set on this term x transpose y. Okay. So what does that mean from a geometric perspective? Okay, first of all, I asked you guys this question in the last lecture. What does x transpose y mean? Someone answered to the question very well from the previous lecture. Yeah, that's a projection, right? So your x transpose y means you can think about your projection, you are projecting y in the direction of x, right? And then you calculate x transpose y, right? So here you are taking the maximum of y in terms of this projection. So you can think about this indicator of function as, I give you a direction x, now consider all the y's in the set C. Which one has the longest projection in x direction? Yeah, okay, yeah. So you have to project that and then multiply by x. Let's assume that x is a sort of we only care about direction. X gives you a unit vector, anyways, right? Okay. Yeah. Then max function is also convex. You can show by definition. Right? If you have a vector of length n, taking the maximum over this length n vector. You can show by definition it is a convex function. Yeah, so let me go through the next slides quickly. I'm slightly running out of time. I want to introduce a concept called epigraph. You can read this bullet point, it's very straightforward. So epigraph gives you a very natural way to connect convex functions and convex sets. So it says the following. Consider an epigraph of a function f. The epigraph is a set which describes x and another scalar t, where t has to be greater than the function value itself. Right? Intuitively, here's a epigraph of function f. So this is a function f. Right? So let's say x is 1D in this case, but then t has to be greater than or equal to the function value. That means this shaded area here, right? So the epigraph is one-dimensional higher than the domain of x, right? Now it says the epigraph of the function is convex if and only if the function is convex. You could see that in this picture, very intuitive, right? When this function is non-convex, that means you can find 2 points, connect them, it is below the function, right? Maybe pick these 2 points, it is below the function, right? And also, if you consider epigraph as a set, pick any 2 points from this set, it is outside the set of the epigraph. Right? So it is equivalent to function convexity, and then you can prove that using algebraic argument. And similarly, there are operations to preserve the convexity of sets. These 4 bullet points can be quite useful when you want to show that a given function is convex, right? Similarly, the motivation is, of course, you can show that by definition or by calculating the Hessian, a given function is convex. But now, if you have super complicated function which have a composition of simple functions, right? So what composition would preserve convexity, right? So here it gives you a manual of deciding how do you show that a function is convex when you have some operation on top of that known convex functions, right? So here, let's say for the sake of the argument, we have non-negative linear combination. If you already know f1 all the way to fm are convex, then you can show that the non-negative linear combinations of those functions are also convex, okay? And pointwise maximization, this probably is one of the most commonly used property that preserve convexity. So if you have a bunch of functions that are convex, now I take the maximum over these functions in the entire domain that preserves convexity, okay? Maybe that is not intuitive if you only read this. Let's maybe plot a simple example. So let's assume we have a bunch of linear functions. Let's say 3 linear functions here, right? Now, if you take the maximum of these 3 linear functions, okay? So now you get what you get here. What you got is this particular curve here, right? So the maximum of any arbitrary linear functions give you a piecewise linear function that is convex. That is a very important property because in many applications, you will want to take the maximum over several linear functions, right? So that is still a convex problem, okay? And similarly, if you take the minimum of linear functions, that gives you a concave function, okay? Of course, you can generalize linear to any arbitrary convex functions. If you take the maximum, they remain convex. I'm not going to show that. You will show that in your homework. It should be straightforward. Just show that by definition, okay? And then partial minimization, it has very strong implications. Probably I wouldn't be able to explain it very well before going to the next few lectures, but let me still try to explain what this means. So if g of x and y is convex in x and y, and C is a convex set, right? So now let's consider this function f of x, which it itself defined as an optimization problem. So g of x and y is convex, and then you are basically solving a convex optimization problem to get the function value of fx, right? Remember, g of x is a convex in both x and y is a convex set, right? By definition, that is a convex optimization problem. You minimize a convex function over a convex set. So by definition, this function itself is itself a convex optimization problem. So this is something called parametric optimization, meaning that this problem is parametric with respect to x, right? So I give you x. In order to evaluate this function, you need to solve an optimization problem here, right? So I give you a different x, you need to solve another convex optimization problem, right? So this has very strong implications because that means the value function of this parametric problem is a convex function, right? So that is a quite useful property, yeah. Then affine composition, this should be straightforward. You take an affine combination of x, then the remaining function is convex. So similarly, with respect to perspective operations, a perspective function also remains convexity. In some of the algorithm, perspective function is used. For now, you could try to prove that, and then if we need to use this property, I will revisit this concept again. Okay. So these are two examples to use the properties we just covered. I'm slightly running out of time, so maybe you could read it after class, right? So if C is an arbitrary set, you consider the max distance, then you could use maximum point by maximum rules to show that f is convex. And then if you use this minimum rule, then you can show this function is also convex. Okay. So the references are this particular book by Stephen Boyd. If you want to read a little bit more details about this, you could refer to this book. And then I also borrowed some slides from this class at Carnegie Mellon where I did my PhD. This class by Ran Tipshirani is very, very well written convex optimization lecture. Okay.